That's done. Then I better pull up my. I keep revising my slides because, there was a time when I would do something and I would be happy with it or okay with it, I guess. Uh, and that was that, right? And I would send it off for publication or what have you, and done. Move on to the next problem. But I tell you what happens, at least what happened to me was older I got, the more fussy I got about what I wrote. And the more demanding I became about what I wrote, demanding about myself, about my students, uh, which I think is not a bad thing. But on the other hand, when you become uh, beyond a point demanding, you pay for it. It's not free. So that's what has happened to me. I keep changing my slides every time I look at them because I think it can be improved here. This should be a little bit clearer, or maybe I wanted to say that I missed it. So I'm going to go back a little bit and kind of uh, remind you of a few things. Not so much because I don't think you got it, but more because um, I want to see if I can better convey uh, how important some of these things are. Um, you see, when you study something, you tend to kind of look at it um, as an outlay of materials that are presumably important to know, which is why it's being covered. And it is not a priori clear which one is super important and which one is more definitional or which one is, uh, you know, maybe convention dependent or which plot should be interpreted exactly how and what the ramifications of that might be. It's not exactly clear. These kinds of learning uh, comes in time as you put the stuff in perspective for yourself. And then, of course, if you're going to teach it, then you want to not only convey it in the order in which you learned it, as you saw it for the first time, if necessary, if appropriate, but you also kind of want to give an idea of what is how important and why. What is the meaning of learning something? What is the meaning of looking at this stuff? Um, what does it tell you in the big picture? Um, these are important questions, and these books cannot answer because the book is designed for thousands of people, right? But when you are talking to somebody, um, that is not designed to be a public lecture. That is designed to be a very specific discussion about your take on it, and that's the reason why you're talking to that person and not to anybody else. So I'm kind of trying to give you that differentiation here. So when you look at this plot, or when you look at this plot, um, even though here the solid line and the dashed line are a little bit separate, but as I told you last time, you shouldn't make much of it because that separation, that distance, that differentiation between the solid line and the dashed line actually comes from the boundary effects. Because when you look at the theoretical solution is designed for certain boundaries which are pushed out to infinity. In a real simulation, the boundaries are not pushed out to infinity. And so therefore some differences will arise. And it is because of those differences that when you look at figures C and D out here, you don't quite see the same level of fit as we would normally like to be able to see. So it's not a big deal. It's not an issue, is what I'm saying. But what is a bigger issue is that when these two solitons collide, as you see here, um, nothing happens. They just slow down and go through each other and completely recover each other's pre-collision status uh, in terms of how much kinetic energy they carry, what width they have, how fast they move, all of that. Because if the motion was different, that would show up in the scale because you're looking at space versus time. For example, if it's slowed down, you would expect a change in slope. But none of that happens. You can take a ruler and run it by. In fact, I don't have a ruler right here, but oh yeah, I have a ruler right here. So I can take a ruler and I can actually physically check it against the screen that there is absolutely zero change in slope. This is my old ruler. If you look at the gray, kind of cone that's coming in, those are sound waves. You expect some sound wave interference, which is exactly what's happening after collision, but not that much. And in fact, when I say they are sound waves, I am actually taking a leap of faith because I don't really know what waves they are. They are a mix of nonlinear and more linear, little nonlinear, more linear. Linear gives you this kind of behavior, but some nonlinearity has got to be mixed in. So it's not entirely linear. It's actually a fairly complicated tale. So why am I telling you all this? I'm telling you all this because if you now take a system and let time roll on by, right? And you have two walls. They'll keep colliding and keep colliding. And as we discussed last time, without worrying about the math, it takes you to something like this, right? So here you can track the collisions. And if you take a different kind of perturbation, here there are two perturbations at t equal to 0, t equal to 0 being at this end. If you take two different kinds of perturbation, one kind of perturbation only, and let it go, but go for a much later time. So this is 10,000, whereas this is only 50 in time. If you go that deep in time, you see that it looks pretty messy. Lots of grays, patchy, dark areas that indicate there is a fair amount of energy in those areas, yet there are solitons. And everything came from one guy. You see, this one guy as it is colliding and everything, it is exchanging energy in some way, shape, or form, not only with other solitons. In this case, there are no other solitons. There's only one original soliton. Everything else that is there came from that tail, isn't it? There was nothing else. Tails colliding with the wall, tails colliding with the soliton itself. Everything is happening because of the tail. And while the leading pulse moves on, what is behind the leading pulse, what's happening to this very strange tail, that is the story that you see in this picture. What else can it be? That is the story that you see in this picture. It's basically mostly the tail interacting with everything else. Now, a soliton interacting with a wall and a soliton interacting with itself is actually the same thing. Because a wall is like an infinite mass. So I go like this, I hit the wall, and I come back. Vis-a-vis, I go like this, I hit another guy, and carry on. So basically, the process is the same because exactly where I'm meeting, nothing is moving. So at that point, the mass is effectively infinite still. So between this and this, there is no difference. This is an infinite wall, right? So what I'm trying to say is that the collisions here are extremely complicated, and clearly the tail has solitons or nonlinear structure embedded in it because that's what gives rise to all these tiny little guys, which is quite amazing. Now, what does all this mean? Does it mean that if I now wait for infinite time, let's say if I could, does it mean that this system somehow the part behind the leading pulse will go to equilibrium? So this is a question that is a legitimate question that one can raise here. And the answer is, wish this was easy to say. Because if you have a soliton, and if the solitons don't really interact non-trivially, and it's a pristine system, there are no impurities to mess things up, the energy of the soliton can't go away. If the energy of the soliton can't go away, then how on earth can it reach equilibrium? Because the very idea of equilibrium is to make a perturbation. That perturbation's energy gets distributed among every possible degree of freedom. Not possible here. So our common sense or reason tells us that it should not go to equilibrium. Yet you see this, which almost says, you never know. But presumably the answer is, it doesn't really go to equilibrium, but a part of it can go to equilibrium-like behavior. And that part of it is that tail part. That tail part is super important. Now, that tail part showed up because of boundary conditions we had. If our boundaries were at infinity, we could have deleted that tail. So there is a real difference between an infinite system and a system with boundaries. And the system with boundaries, whether it's periodic, whether it's fixed end, can give you this. So if you are looking at this problem from that lens, it is impossible to reject the idea that even for a quote-unquote integrable system where a solution can be found, once you bring in the boundaries, the problem can still be very, very complex. And this is an example of how complex it can be, even for an integrable system. Now you can see, I hope, why people obsess about the consequences of non-integrability and integrability. Because if a system is integrable, you expect a certain modicum of good behavior, which doesn't seem to be the case here. So how much difference is there between an integrable and a non-integrable system? The answer is not that easy. It depends upon the system. It depends upon the boundaries. It depends upon how long you wait. But at the end of the day, the integrable system is not expected to go to equilibrium, whereas, sorry, the integrable system is not expected to go to equilibrium, whereas the non-integrable system might be expected to go to equilibrium. So this is something that we cannot really trivially forget. Now, to make matters worse, if instead of perturbing a single particle like we have done here, suppose I perturb every particle and with a distribution of velocities, and that's when I showed this plot last time. That gives you something like a rogue fluctuation. Not a rogue wave, but a rogue fluctuation, because we're looking at kinetic energies. So even for an integrable system where things are supposed to be okay, something like this can happen, which is quite remarkable. And this opens a lot of issues, many of which we don't know the answers to. And this particular study that I am showing you, that we did, is the subject of a paper that we will submit soon. But the paper is so jarring to me that I have been like I said in the beginning of the lecture, that I've been actually super cautious about submitting it and making sure all the right words are there because I don't want my collaborators and colleagues in the field to come and say, "Hey, I looked at your paper, but it makes no sense. Have you lost your mind?" I want to be able to answer them. Otherwise, it will be mighty embarrassing, right? But I mean, this particular study, to the extent I know, nobody else has done it. People have done related studies, but this kind of study people haven't done for the simple reason that when you integrate the equations of motion that deep in time, it is super important that your integration algorithms are very good, and not too many people are experienced at it. We are. This is all I do in terms of research most of the time. So our integration algorithms are very, very polished over decades and decades of work. So we know uh, how to be careful, let's say. That doesn't mean we're always right. We know how to be careful. All right. So so coming back to this question that I put up on Tuesday, uh, my friends who are distinguished applied mathematicians who work on these problems often, uh, they would replace their integrable system, their non-integrable system, uh, by an integrable system. And the attraction to do this is non-trivial. The attraction to do this is non-trivial because you see, when you can integrate a system, you can do analysis. So then what happens is you can take a system that is non-integrable, for which analysis is by definition difficult to do, and approximate that with that of an integrable system. And then open a more refined question that, this is a problem. If I put an integrable system as a solution, I get that much of the problem, this little much I can't. It helps define some kind of range, tiny range, where your solution may not be right, but you can still get the big picture. That's the idea. And it's a very good idea, not a bad idea at all. But still, there's a lot of controversy over it because uh, do you miss out the baby with the bathwater? That is the question. And many people would say probably not. My experience is yes, you do. You do miss out the baby with the bathwater, but that's my experience. I haven't gone out and you know given a public lecture to applied mathematicians on this. If I do that, I'm sure it'll result in tables and chairs being thrown at each other because people wouldn't, by and large, not agree with me. Okay, so we discussed about, you know, what kind of a person Fermi was and how he attempted to solve these problems. We also talked about how Zabusky and Kruskal took the alpha problem, meaning this problem, and and took it to the KdV problem and solved it and showed that solitons are there. And then we talked a little bit for fun about the great accomplishments of Fermi and how very distinguished he was as a thinker. And then we came to another take on Fermi and uh, the problem of Fermi, Pasta, Ulam, and Singo by the great Joe Fox. Joe Ford, I'm sorry. Uh, so having come here, I want to kind of slowly go over Ford's paper because Ford's paper, I think, is a very defining paper in the field, um, and there is a sort of a no nonsense aspect to this paper because he says what he thinks. Okay, um, and I want you to you know see that. Um, is not what I want. Okay, fine. Actually, if this is what I want, then I can't see anybody's face. This is, maybe I'll just park you guys at the bottom here of my screen. So after much back and forth, FPU decided to numerically integrate the weakly nonlinear fixed end chain. So n-1 moving masses. This is the Hamiltonian written in canonical coordinates. As you can see, everything is here, particle mass is here. Particle numbers are given by small k, which used to be quite common in those days. But nowadays, probably not so much, because k is usually, small k is a symbol that is often used for wave vector, right? So we don't really use small k so often, but here k is just a regular particle index. This is an alpha model, as you can see. There's an alpha sitting out here. And the K, the coupling for the harmonic spring is set to 1, thereby fixing the fact that the harmonic interaction is dominant and alpha is the one that's being typically varied, where the presumption is that alpha is much less than 1, typically, meaning this coupling. So I don't want to spend time on this slide, because the thing to remind you here is go back to slide 68, I think, if I recall correctly. I've done this with you guys before. Yes. You remember the fact that we put the harmonic oscillator chain in the very beginning in normal mode coordinates a long time ago. This was the paper, 1985 paper. Right. So that's the same thing being done. Okay. So when you put it in normal mode coordinates, then you can put the Hamiltonian in terms of normal modes, where the normal modes capital Q and capital P are related to the small q and small p by Fourier transforms. That's what we had done. We had seen. So the same thing is being done here, so that nothing different. Excepting it's written a little differently by Ford, and Ford hasn't gone into the mathematical detail aspect of it. But so this is really the Fourier transform bit, and it takes out the nature of the amplitude and so on. But that's not important. The point is it puts the Hamiltonian in this form, where A, in this case, ties to Q and A dot ties to P. So he writes it in this form. This is the alpha term. So x cube is AK AL AM. This is a coefficient. And AK square is, of course, the harmonic term. And AK dot square is the momentum term. So the language is a little bit different, but essentially the same thing that I showed there, excepting it's written now for the alpha FPU problem. So anyway, now comes the important thing that I want you to understand. To understand why, to understand this picture. Remember these pictures we have been seeing from time to time, where we are talking about mode 1 and mode 2. And I think Tony had a question about what it means and so on, and we discussed it at the time. And so I want you to come back to Ford's take on it, because it is very, very interesting. Okay. So at time t equal to 0, because Ford did a much deeper study of exactly what they did. At time t equal to 0 in figure 1, meaning that figure, and n equal to 32, fixed end chain governed by Hamiltonian 1 with alpha equal to 1/4 was started at rest in the shape of a half sine wave given by this. That's half a sine wave. That's what was let go. In other words, only the fundamental harmonic mode was initially excited and given amplitude A1 equal to 4 and energy E1 equal to 0.077 in system units. During the time interval small t between 0 and 16, in figure 1, where T is measured in periods of the fundamental mode, modes 2, 3, 4, etc., sequentially begin to absorb energy from the initial dominant first mode. This is expected. Basically, that's what he's saying. If you do a short time analysis or high frequency analysis, this is what you would expect. Following this, the pattern of energy sharing undergoes a dramatic change. So following this, where you see initially only one was given, but then two started, then three started, then four started, then five started. Sequentially, they started. But it went up until about six. That's what he's saying. Energy is now exchanged primarily only among modes 1 through 6 after that. So it's almost like 1 and 6 are talking to each other. 2, 3, 4, and 5 are not talking to each other very much. How bizarre is that? Incredibly enough, the energy sharing pattern revealed in figure 1 for this few body and harmonic system is remarkably similar to that observed in the laboratory for a few body harmonic system. For a few body harmonic system, in the lab, if you were to do this, he's saying, it'll be just exactly about the same, as if the harmonicity didn't exist at all. So indeed, the motion of this nonlinear system appears to be not only almost periodic, but perhaps even quasi-periodic. The first major near period, what they call FPU recurrence of the motion, occurs at T of the order of 157 fundamental periods. So let's see what the next one is. It doesn't nearly go as deep, but that's far, far into the simulation. And this is the case where alpha is 1. So clearly more energy is being given to the first mode. And naturally, there is a little bit more action going on. This one is a little bit more sluggish from what I can tell. This is, of course, 30, and this is 18. So quite a bit more action is going on. But he's saying that the recurrent state behavior is coming far deeper in time than is actually shown here. Here, the energy in the fundamental mode returns to within 3% of its value at t equal to 0. Wow. So it regains almost 97% of its energy. FPU immediately recognized that these results were simply astounding. First, they appear to violate the canons of statistical mechanics, which assert that this nonlinear system should exhibit an approach to equilibrium with energy being shared equally among all degrees of freedom, of course, at late times. But it's not going in that direction. It's stuck. Or is it stuck? Is it really stuck, or it appears to be stuck for a short time? And then what is a long time? Is that even accessible with machines, right? But even more astonishing, they seem to invalidate Fermi's theorem regarding ergodicity in nonlinear systems, because Fermi himself thought about this problem earlier. And in 1926 or 21, he wrote something on this. I actually looked for that paper. The paper is written in German, but I actually asked our library to see if they could get it, and they haven't gotten it yet. And it was about 10 days ago. Indeed, Fermi is said to have remarked that these results might be one of the most significant discoveries of his career. Now, this is exactly the reason why I gave you this slide to list the significant discoveries of his career. Right? Beta decay, neutron bombardment to explore transmutation, the first nuclear reactor, discovery of Fermi's. I mean, these are the level of discoveries that Fermi made. And that man felt that these results might be one of the most significant discoveries of his career. He had only remarked it, I think, to Ulam. Now, Ulam lived a long life, so Ulam was in a position to relate Fermi's thoughts to others. Unfortunately, Fermi never had the time to write it because he died so young in 1954. So this is kind of where things were in 1955. And the community of physicists were completely lost with this result. Whoever saw it, whoever heard it in due course, they couldn't make head or tail of it. The expectation is very well captured by Professor Jackson's book. Atlee Jackson wrote this very famous two-volume book called Perspectives in Nonlinear Dynamics. I think I mentioned this to you guys. It's a two-volume Cambridge University book that came out in early 1990s. Jackson has passed away many years ago now, but he wrote this, encyclopedic books on the subject, and he discusses all the nonlinear dynamics problems in meticulous detail and works them out. In particular, are his sketches in the book, which are quite remarkable. So he wrote, FPU studied for these two amplitudes, the two different Hamiltonians, and for several n values, 32 and 64, which at the time was quite big. They initially put all energy in k equal to 1, meaning the first mode, as we just read, and wanted to know how long it takes for this energy to get equally distributed to all the other modes. Of course, this was the expectation. And so they expected the following. And this following is this. I took it from the book, actually. So this is the energy in some units. And this is the time. And this is the energy in the first mode. And the expectation was that the energy in the first mode would quickly decay out, and the rest of the modes will get it. And then eventually all the modes will get it. That was the expectation. So this sketch by Jackson essentially captures what was the expectation. And that is the reason why I'm showing this to you. So let's now go back to what Joe Ford said, because that part of the history is also something very, very revealing. Because if you understand what Joe Ford says next, you will better understand what I'm going to tell you after that. So here, Ford writes, this is about all the other people in the community who saw these results, offered many resolutions unsupported by the slightest shred of hard evidence. He's being very critical of his colleagues. Of course, the vast majority of readers were simply puzzled by the FPU manuscript. Of course, it was not a refereed paper because it was never submitted and had no explanation to offer. Regardless, everyone found the preprint to be quite startling and equally fascinating. However, almost no one recognized it as a harbinger of a new era in physics. What is this new era? The birth of nonlinear dynamics as a legitimate field that happened through this paper. But in fact, the FPU calculations exposed a genuine paradox whose unfolding resolution has unleashed winds of change destined to blow far, far into the 21st century, which we are living through. In this personal retrospective, we shall gauge these winds and seek to place the work of Fermi, Pasta, and Ulam in proper historical perspective. I can't tell you how much I appreciated this kind of candid presentation by Ford, because when I was learning the subject, like all the other people, I also was very, very puzzled. I said, oh, how is that even possible? And what is the explanation? And what does it mean? If such a simple problem can confuse people so much, what do we know? Do we not know anything about nonlinear systems? And really motivated me to look into these subjects. So FPU expected the motion of their coupled system to be stochastic. Here, stochastic means the following. Stochastic means that FPU expected the coupled oscillator system to end up with uniformly distributed energy at time t goes to infinity, because that would take it to equilibrium. So stochastic here is a code word for a journey to equilibrium. Whereas their computer calculations revealed the motion to be highly ordered, perhaps analytically solvable. But should we not be startled that researchers as sophisticated as Fermi Pasta-Ulam would make such a misjudgment some 300 years after Newton? He asks a very candid question. I mean, how could Fermi, Pasta, and Ulam screw up like this? That is basically what he's saying. I mean, this is a massive screw up. They thought that they would get this result. Couldn't they somehow guess? And then he answers the question himself. For given the FPU Hamiltonian, does not dynamics provide an easily applied test predicting the character of the motion which ensues? In FPU's defense, let us quickly admit that there is no such test. Only folklore supported by prejudice. In other words, he lays it on everybody, including people like us. You guys don't know shit. That's what he's saying. You guys don't know shit. Until you solve a problem, you don't know what's going to come out. If Fermi, Pasta, and Ulam couldn't tell, nobody can tell. And he's darn right about it, because as I will show you now, what happens only adds to the mystery. Now, before I say that to you, this was, Ford wrote this paper in the which year is it? 1992. So he's writing a paper in 1992, which is obviously quite updated. And he's very much aware of much of the literature that has now emerged until 1992. The situation remains very unresolved. We, of course, know a lot more. Now, among the literature that had already emerged at the time was this paper. A very famous paper, actually, in the field, with close to 300 citations by now. Of course, it is old. It's about 31 years old, by physicists from Italy, very good physicists, actually. Equipartition threshold, the word. Equipartition threshold in nonlinear large Hamiltonian systems, the Fermi-Pasta-Ulam model. And this is, of course, Roberto Levi, Professor Roberto Levi. And then there are all these other distinguished names also who contributed to this paper. I won't read this for you. I'll tell you what it is I'm trying to say. What they are saying is, they're saying that, look, if you excite this Fermi-Pasta-Ulam system at very, very low energies, it may never go to equilibrium. The key word here is may. It may never go to equilibrium. And the reason why they are making this suggestion, and thereby implying that if you excite it at higher energies, it will go to equilibrium, and hence the word equipartition threshold. That means if the energy is above this threshold, equipartition is possible. Energy is below this threshold, equipartition is not possible. And let me add to that, that this confusion is alive and well as to where this equipartition threshold is and whether the equipartition threshold even exists, even today in 2026, April 23rd. This is their very important plot. The plot should make no sense to you right now. So let me try and explain to you to the extent I get this plot. I personally don't like this plot. I don't like this plot because I don't like to plot things which are run until a certain time and then blurted out. without the time details in it, and the time details are not in it. So these are the various system sizes they looked at. Epsilon is the energy. And as epsilon goes down, which means that as the energy of the system goes down, this on the y-axis is an approximate count of the finite number of modes that are getting excited. It's not really, it's a processed quantity, but it is approximately supposed to capture the modes that are getting excited. Is it really? That modes that are getting, that are not sharing energy, I think is a better way of stating it. Here you can see that as epsilon is increased, the energy sharing, basically all the modes can share their energies. And so therefore, this number goes to 0. It's a funny measure, I'll come to that. It's a measure of how much energy is sitting in various modes. That's how I'm trying to capture it. It's actually a version of Shannon entropy. That's really what it is. But you guys may not be familiar with Shannon entropy, but physically what he is measuring is how much energy is sitting in the various modes. All the energy here is sitting in low modes. Less energy is sitting in basically the lower modes, and then no energy is sitting in the lower modes, meaning it's equipartition. So in this case, he's basically saying that when this energy epsilon exceeds 0.3 or so, equilibration is possible. You should be able to see equilibration. That doesn't mean it's easy to see. That means if you wait long enough, the signatures of equilibration, equipartition should come. But once you get below 0.3, the energy begins to localize. This was the story that Roberto Levi and company kind of put out in 1985 in a very important paper. And so if you ask people in the community who are experts, they'll say, well, you know, here is a very important paper by Levy. This paper has been checked by many people, and this is a result they had claimed that your energy has to be above a certain threshold for you to be able to see this delocalization, if you will, energy being fully shared. I don't want to claim anything from my side as one of those little people who worked on it, but between the three of us, I never believed that this paper was quite okay. Not because I think that Levy et al. Can make a mistake, but more because it physically means to me that there is no ground for a threshold here. To the extent I know these problems, because I've only done dynamical problems and nothing else in my life, so I have a little bit of understanding and appreciation for how nasty they can be. I just couldn't find any overwhelming reason why there should be localization or non-ergodicity below a threshold. But then again, it's my guess. You know, as Ford has pointed out, all these pundits are no good, so I am no good. But this was my guess. Then in 2015, 30 years later, came this paper, Route to Thermalization in the Alpha Fermi-Pastor-Coulomb system. Exact same problem. This appeared in Proceedings of National Academy of Sciences because it's such a controversial topic, and they made a very interesting case. And in this paper, the first author is this guy, Miguel Honorato, and then this is Yuri Lvov. Yuri Lvov is a very important name also. You know, a great deal of the work in nonlinear dynamics, especially in the case of fluids, was done by Sakharov, Sakharov. Sakharov, of course, as the name suggests, was one of the Russian great applied mathematicians. Sakharov later moved to University of Arizona, Department of Mathematics, and I believe he passed away in 2024 or so. So Ilvov was Sakharov's student and one of Sakharov's later students. He's a professor at Rensselaer Polytechnic Institute, and Michele Onorato is a professor in Torino, in Turin, in Italy. So this particular group, they actually took the exact same variable that Levy et al. Took, this quantity that they called eta, but as far as I can tell, their paper left me even more confused with regard to this quantity, but I'll still tell you what it is. So just like in Levy's case, in Onorato's case, S of t is what he calls the eta. S of t, instead of plotting it against energy, is plotting it against time. But this S of t is the same. S of t is a measure of how much energy is sitting in various modes. So if all energy is in one mode, S of t goes to 1. That means total energy in mode 1 are the same. So the 2 divided takes you to 1. Think of it that way. All the energy, a particular mode has a teeny tiny little bit, then it's a very tiny number. So therefore, by that logic, as you go towards equipartition, then your S of t should go towards 0, right? Because each of those guys, if there are n particles, suppose the n is 500 particles, then each of those modes, even if it's harmonic, will have 1 over 500. If it's nonlinear, there are probably infinite number of modes. So therefore, the amount of amount of energy sitting per mode should go to 0. That is the logic. This logic ties to what is known as Shannon entropy. The entropy that you learn in statistical mechanics is not Shannon entropy. That's thermodynamic entropy. Shannon entropy has a slightly different definition. I'll tell you that. But this is the sense it conveys. So you see, at very, very early times, all the energy is sitting in the first mode. So if all the energy is sitting in the first mode, it shouldn't surprise you that this S of t then is very close to 1. But as time progresses, this S of t slowly goes down and then rapidly drops down. So beyond a certain time, beyond, let's say, about 10 to the 4, 10 to the 5 t here, there is a very sharp drop in the value of S of t, thus suggesting that by the time you get to about 1 million in t, or a little more, you're probably inching towards a possible equilibrium state. So very, very definitive proof from these simulations that there is no cutoff. There is no cutoff. You just have to wait longer, which is exactly what I had guessed, because whenever you introduce a cutoff, there should be a real logic for it. In this case, there is no real dramatic logic for it. So I wasn't expecting one. And this paper was, when I saw this paper, I was going to the colloquium that day. And I must tell you that I had very mixed emotions. I had very mixed emotions because one of my thoughts was, damn it, I wish I did this study myself because it could have been done. This is what I was expecting. And then excitement, because this is exactly what I was hoping one would find, right? This was my intuition too. But there is something fascinating going on in this plot. What is fascinating is, see the last two legend items. Thoda. Thoda is not ergodic. Thoda does not go to equilibrium, right? And they claim that this red line and this, whatever color you call it, I call it light blue, red line and this light blue line suggests that it does not actually go to equilibrium. Whereas these other guys do. I can't tell. I don't know what I'm missing here. I can't tell. So Actually, it should not go to equilibrium. But what I'm trying to say is that an integrable system can actually end up looking like it goes to equilibrium. And that's what we found in our paper. So now I'm very excited to actually submit our paper and take the wrath of the referees because nobody's going to be happy about what we have to say in that thing. Yes, Tony.
Don't even see the dotted lines on this. Are they overlapped with the solid?
Yeah, I think so. I think that.
Okay.
Oh, wait a minute. No. I'm sorry. The dotted line is sitting right here. So
Oh.
it has come down to 0.01, 0.001 here.
Oh, okay.
So it has gone down a lot, hasn't it? It has gone down by 3 orders of magnitude from 1, but they're looking at really super tiny numbers. Now, I don't know why it's 0.001. Uh, this is 10 to the minus 1, they're saying. So I couldn't explain why it is here. Maybe it goes down even later. I don't know.
Do they mean that black horizontal line down at 10 to the minus 3?
No, but they're saying Toda on the side, right?
Yeah. Mhm.
So let's see what it says. Um,
But that's aren't this graph on log scale?
huh?
This graph is on a log scale.
On a log scale. But 10 to the minus 3 should be around here, right?
Mhm.
This is 10 to the minus 3, isn't it? So
There is a darker,
horizontal,
yeah, there is a
huh?
horizontal line there, I guess, that's slightly darker, but then I don't know what the dotted line is up top.
One possibility is that this comes down much later. They may have made an estimate, or maybe it doesn't come down. I thought that they get to 0.001, but that's not what. But you see here they say 1.02 10 to the minus 1 Toda. 9 times 10 to the minus 2. They're very close, obviously. I think that's what this is. So some level of spread is seen at whatever energy levels they examine. Some level of energy dispersion is definitely seen, but obviously not at this level. I think what they're using this black line for is for actually saying the equipartition time. They're saying by the time you come over here, the number of for S of t is so small that it's actually equipartition. So they're making a call here from their system particulars that by the time you get to this intersection with the solid black line, you're essentially in equilibrium. So that is applicable to the non-Toda cases. But the Toda case itself is over here. So Toda case itself is therefore certainly below 1, but not much below 1. That is my take. I actually thought this tells you a little bit about how bad my eyesight has become, that this is the I actually originally thought that these two are the Toda cases, but no, because these two solid lines are these two, and this is that one. Okay, thanks, Tony. If you hadn't pointed it out, I would have been in the dark. Okay, so let's get into this S of t a little bit. It's an interesting measure. S of t is basically called spectral entropy. And the spectral entropy definitions in the paper by Onorato et al., this paper, versus in Levy's paper who introduced it, are different. Okay. And I believe Levy actually has defined it correctly with a minus sign, and these guys actually don't have a minus sign. So Levy has a minus sign here, whereas they don't. So there may be some subtle difference in how they define the quantity. I don't know. But here you can see it's basically a fraction of how many modes are actually involved divided by the total energy carried by all the modes. So if all the energy is sitting in the first mode, this over that is going to be 1. And then log of 1 is going to be 0 in this case. So you have to avoid all the energy sitting in first mode, but you have to then go from the second mode onward. I think that's how it's set up. The first mode k equal to 0 is not involved in the dynamics here, it says. They may have set the first mode to k equal to 0. Since they haven't stated it here, I can't tell. Either way, I mean, the meaning is as follows, as I said. If all the energy is sitting on the first mode, then this spectral entropy goes towards 1, like here. And if all the energy is distributed, then the spectral entropy becomes small because tiny energies are sitting all over. And a lot of tiny numbers added up still makes it a tiny number. And that's basically what it's saying. I'm not very used to this Shannon entropy measure, to be honest with you. I mean, people work with Shannon entropy a lot, but I haven't worked on it. Worked with it rather. This is a picture of how the various modes carry energy. So as you can see, for k equal to 1, energy spectrum at different time steps from numerical simulations of the alpha FPU system. Black dots correspond to the initial condition. Okay. Blue triangles correspond to an intermediate stage, and red squares correspond to the final thermalized spectrum. Note that energy is presented in a linear scale. So this is the final thermalized spectrum, starting from here, going like that. And this is the intermediate stage. Some distribution is there, and this is at t equal to 0. Not super clear, but this is a story of the mode distributions. Okay, so what do we see? What we have seen today is what I couldn't discuss earlier, which is, to the extent, without getting your hands dirty, how the energy sharing is happening in this very, very famous Fermi-Pastor-Ulam system. What you do not see is as follows. You see, when you take a harmonic system and you give it a push, the whole system jiggles around immediately, right? It just starts. You can well imagine taking a mass spring chain and giving it a bit of a push in one point, and before you even can blink an eye, everybody's excited. Now, that's how harmonic systems behave. However, if I take a bunch of balls along a line, whether they're connected by springs or just hard spheres simply touching each other, and if I give it a kick, I will not expect a jiggle of the entire system necessarily, especially if the connections between the masses, the interactions between the masses, are not linear, meaning not harmonic springs. What happens is that this push that I gave at one end, this push propagates like a pulse. That's how energy moves through the system. To bring up that point, I will actually take you guys to a paper we wrote some years ago with this PhD student. And this is the title of the paper: Solitary Waves and Localized Nonlinear Excitations in the Strongly Nonlinear Beta Fermi-Pastor-Ulam Single Chain. So what do I mean by strongly nonlinear? What I mean by strongly nonlinear is that in this case, the harmonic term is the weak term. The xi minus xi plus 1 raised to the power 4 in the Hamiltonian term is the strong term. So that is a strongly nonlinear beta Fermi-Pastor-Ulam system. So in that system, we gave a kick. Okay. we gave a kick. And the kick travels from left, let's see. Kick is traveling from right to left. So initially, when a kick is being given, I think the way the measurement is done, this is early time, this is late time. Let's read it carefully. Kinetic energy of the propagating pulse taken as a function of time as the wave passes through a particle far away from pulse initiation. This is the value of the spring term. See, spring term here given, alpha over 2, instead of 1 over 2, it's alpha over 2. So the strength can be adjusted, and this is beta over 4, which means this is the nonlinear term. And if beta is much larger than alpha, that would take you to what would be the strongly nonlinear regime. So in this case, imagine you are sitting at a particle. Imagine this is a long chain, excitation has been done at one end, you're sitting at a particle. So what will happen? What will happen is, at early time, you will see the fast-moving pulse come because that will be the leading pulse. And at a later time, you will see whatever is the trailing end of it come, isn't it? So I have a long chain, I'm sitting here, you have perturbed at this end, let's say. What I'll see first is the fastest moving pulse go by, and then I'll see the smaller pulses go by, or the tail of the oscillations go by. That's what we are seeing here. So in A, if you are sitting on a particle far away, the first thing you will see at early time, T about 700, is a massive pulse, big energy flowing by. And then somewhat later, at T of the order of 1000, there's a tiny spike. The difference between other cases and this one is that in this case, alpha is 0. There is no quadratic spring. Okay. There's only a quartic spring. And what the system is telling you is that if you have only a quartic spring, all the energy propagates necessarily as some kind of a soliton or a solitary wave. We don't know which one. All the energy propagates like that. If you now turn on a very tiny alpha, in fact, it's alpha equal to 0.01 in this case, as I can see. In B, alpha has been increased to 0.03, and you can see that a very, very tiny tail is beginning to form. So I'm sitting in this particle far away. The first guy that goes by is this big pulse, but after that, there's this tiny tail, and look at how long this tail is. The tail keeps me oscillating literally forever. And if I jack it up a little more, if I jack it up to alpha equal to 0.05, so tiny, tiny spring strength is turned on, and look at what happens. There is a very significant tail that is developed. And by the time you jack alpha up to 0.1, not only do you have an even more significant tail, the leading pulse is now part of the family. It's like the big brother, but it's part of the family. The two have joined up. They are no longer separate like you had in part B, in figure B. There was this, there was a gap, and then this guy. By the time it was 0.05, they were beginning to merge up. By the time it's 0.1, the tail and the head are very much part of one unified thing that's moving through. Where is all this physics in the alpha Fermi-Pastor-Ulam system? Okay, you don't see that. And the beta Fermi-Pastor-Ulam system was not very well studied until much later. So what I'm trying to suggest here is that this system, whenever you have a nonlinear term in the Hamiltonian, like you have here, like here. Sorry, like here. This nonlinear term generates some kind of a soliton/solitary wave for you. This term generates oscillations for you. And all I'm trying to show you is that the moment you turn on the harmonic term, you get lots and lots of oscillations. If you turn it completely off, you get a soliton or a solitary wave. We'll see. Actually, it's a solitary wave. It's not a soliton. But we'll come to that. So this physics, by the way, is actually embedded in the Fermi-Pasta-Ulam system. This is embedded also in the alpha Fermi-Pasta-Ulam system, although they did not see it. Now, can you imagine, can you guess why they didn't see it? The reason why they didn't see it is because what did they excite? Modes. They excited modes. And when you excite modes, as you can see in the figure D here, if the harmonic term is very strong and the nonlinear term is very weak, the modes overwhelm the nonlinearity. It is impossible to see the effect of nonlinearity. It is impossible to see the soliton type behavior. And that is the reason why they kept missing it. That is the reason why for decades and decades, people weren't sure about how the soliton business comes. But let me take you back to something that I've been showing you time and again, this plot. Sorry, this slide. What did Zabusky and Kruskal give us? Zabusky and Kruskal said, you take Fermi's problem, Fermi-Pasta-Ulam-Singu problem, take the alpha term, don't take the beta term, take a continuum limit, you do some picking and choosing of terms, you can't do a rigorous thing, but a near rigorous thing with slight dressing up, and lo and behold, what pops out is a Korteweg-de Vries equation that gives you a soliton. So this system must be having some soliton. That was the message of Zabusky and Kruskal. And this led to the birth of the study of solitons in the physics community in the 20th century. Not that people didn't do it, but not that many people did it. So what I'm trying to show you from our work is something that is showing you the mix of the soliton and the oscillations. Accepting that instead of playing with the alpha problem, I've gone to the beta problem. And the beta problem is the strongly nonlinear problem, but the soliton is the dominant energy carrier. And these oscillations actually disperse the energy. And that is the reason why whenever there are oscillations, energy dispersion is not a problem. However, whenever there are, so energy dispersion is not a problem, but the nonlinearity must come in such that equilibrium is possible. Because in a harmonic system, if there are n oscillators, there are only n modes, period. Whereas in a nonlinear system, even if you have one particle where there is a nonlinear term, there are infinite modes. You don't have to take n going to infinity. N equal to 1 will still give you infinite modes because you need infinite modes to make a soliton also. So I don't know how much of it you're able to absorb, but what I'm trying to tell you is that these systems have solitons. That's what Zabusky and Kruskal pointed out. And that's why we see what we see. Okay, so now let us try to get a little bit more sophisticated. We have a few minutes. And I'll show you a paper that may seem quite unrelated. That is a paper here from 1999. Very distinguished group of people led by Katja Lindenberg. Katja is like a mentor and a friend of mine, very close friend. And and this is a work done with Katya and her postdocs and visitors. So I know almost all, actually, I know everyone here. If I remember correct, in fact, I visited Katya shortly after this paper. And if I recall correctly, this is Massimiliano Esposito, who is now quite well known. He is a professor, if I recall, in Belgium, probably. This is Upendra Harbola. Upendra was Katya's postdoc, and Upendra wanted to do a postdoc with me. I unfortunately had no money at the time, which is my typical situation. Half the time I do such crazy things, I don't have much money. And Upendra eventually returned to India. Upendra is a professor, by the way, in Indian Institute of Science in Bangalore. This is Alexandre Rosas, who was somebody who learned some of this stuff also from me back in 2001. And then this is Aldo Romero. Aldo is a distinguished professor at West Virginia, and he was at the time visiting Katya. So they did a study, and Katya is very good for doing extremely in-depth studies of things and making it simple. Okay, so here she took what is essentially a harmonic oscillator problem, a chain of harmonic oscillators, and pointed out that, look, the solution that you take, which is all this stuff here, part of this paper delivered the message that all this thing that you've been showing us time and again in the books can be beautifully captured in the fact that the oscillation of a particle, single particle, through which a harmonic harmonic wave is passing through, which has been perturbed by this n harmonic oscillators, can be captured as an integral of a Bessel function. A very, very beautiful result. In fact, it is the integral of the Bessel function, I might argue, that is giving you this beautiful behavior here indeed. This is the Bessel function type behavior. In fact, the reason why you don't see the negative is because we are plotting kinetic energy. So we have essentially done a mod square of the first derivative of x of k or n, whatever Katya used. This is what Katya used, x of n of t. You do a derivative of this and you do a mod square and you essentially get a Bessel square. That's what we have. So Katya beautifully pointed out that you have a Bessel function solution for a particle in a harmonic potential, along with other things in this beautiful paper. That's why I thought I'd show you. So what we did was we said, okay, fine. We were interested in this study, of course. And we said, well, Katya has already solved the harmonic piece for us. We don't know what the quartic piece should give us because nobody knows. It's not a solvable problem, but we made a gentleman's guess. And the gentleman's guess is that we will consider this solution, the solution for the quartic part, to be a hyperbolic secant square solution. Because everywhere we have done soliton so far, we saw the set square behavior. Remember, even if I take you back to Zabriskie-Kruskal problem here, what do you see? Set square, right? 3v set square, square root of v over 2, blah, blah. So it's got to be a set square somehow. So we took a set square solution to see if we can fit it. But we took Katya's solution here, sorry. We took Katya's solution here for xn of t otherwise. And when we put both the pieces in with some tweaking of the coefficients, look at what we got. This is a solution to the Fermi-Pasteur-Ulam problem, but in the beta Fermi-Pasteur-Ulam problem, not the alpha. The quartic term. In this case, the alpha term first has been turned off. So there is no Bessel function. This is just the set square solution. As we show, set square but now it is set square of AZ plus BZ cube. Z is x minus CT. It's a co-moving coordinate. So AZ plus BZ cube. So we wanted to introduce a polynomial argument, the set square, just for fun, because the set square AZ alone won't fit well. So we tried this, and lo and behold, up to 5 orders of derivatives of our solution, as you can see here, I think the red line is our solution, and the dashed line, or rather the dot dashed line, is from simulation. And if this is not impressive, I don't know what is. We just fit it to 5 orders. Isn't that amazing? And all because we took Katya's solution and this solution. In this case, we turned off Katya's solution, just took our solution, and this is what you got. And these are the coefficients here. We took the initial velocity of the perturbation to be 0.4, and then we took the coefficient before the set square to be this, and then A to be this, and B to be this. That's it. As you can see, A is more important than B, but B is still not trivial. C is not needed. C doesn't make the solution any better. So 5th order term in Z is not needed. And I will not show you how good it is, but let me just show you the solution is so good that we have evolved our system with this solution, not simulationally, but with this solution as the input and simulations after that, 5, 6, 7 decades later in time, and the predicted and the simulated sit on top of each other. You won't be able to make the difference. So this is how important that solitary wave in this case is. And that's what's going on here. And I'll finish with this picture. These are the solitary waves coming towards each other. These are the solitary waves after collision. And look at this mess here. This is non-integrability. In other words, they interact. They produce new things as they travel through each other. This scattering is what drives the system eventually to equipartition. And this scattering, I claim, is happening in Fermi-Pastor-Ulam's alpha problem also, which is why it should go to equipartition. Zabusky and Kruskal's solution of a soliton is inaccurate, but shows that the fact that solitons are there, but in reality, it is not an integrable soliton. It is actually a non-integrable solitary wave that is sitting in even the alpha problem, which is why always the problem will eventually slip off to equipartition. I don't know how much I've been able to convey to you guys today. I hope you got the gist of what I was saying. I'll work through some other aspects of this very important problem, which is still evolving. As you can see, it's 70 years since, in fact, 71 years since Fermi-Pastor-Ulam's work, Fermi-Pastor-Ulam-Singhou work. But the subject is alive and well, and the subject has become murkier and more difficult and more challenging over time, which is why I'm teaching. Otherwise, I won't even be teaching this class. So let me close here, and we will dig deeper into the physics of nonlinear systems. Let me leave you with the statement that we don't really know much about the physics of nonlinear systems. Each of these studies or sets of studies that I'm trying to put together for you are designed to illustrate, if you will, the blocks that make a pyramid. Okay. The pyramid hasn't been made, but some of the lowest level blocks are beginning to come together. And Fermi-Pastor-Ulam's work was the very first block, and there may be 30, 40, or 50 other blocks that have that can be captured as progresses. Ours also is one of those blocks, I might add. And so I wanted to kind of give the context properly, because otherwise you don't really get what is being done. So next week when we start, I'm going to continue along this track, and I'm going to try and hopefully give you more clarity and also take you to some of the solutions that can be constructed explicitly for whatever systems that we are dealing with. Okay, it's late for Vivek. It's time for Tony to rest up a little bit. So we'll close here. Okay. Questions?
I definitely have some questions, but I got to think about them more. I don't know if I could formulate one.
Yeah, formulate them. I'm gonna send you guys a PDF of how much we have done so far
Right.
today.
Yeah.
Okay, that we can take a look. All right, bye-bye.
Yeah. Thank
Thank you.
you. Have a good day, guys.